Thank you all for joining us here for our second PRISM seminar of the spring 2026 semester. I have with us today Dr. Sanford Student. So Dr. Student is an assistant professor of educational studies and research methods at the University of Delaware, working in educational measurement, psychometrics, and quantitative methods. His methodological research focuses on the role of measurement in the analysis of growth and change, with particular emphasis on the ways in which psychometric decisions, which are often somewhat siloed, shape the answers to substantive research questions. Alongside his methodological research, he contributes to substantive research in diverse areas, including educational assessment, early literacy, child language development, cognitive decline in older adults, student motivation, and much more. Dr. Student also has the honor of being the last friend I made in person before COVID lockdown began. So I'm incredibly excited to have him with us today. So please join me in welcoming Dr. Sandy Student.
Thanks, Clint. Really excited to be here. I do want to make sure that I share my screen properly. It's the riskiest part of giving a virtual talk, right? So do I have the first slide up and it's not in presenter view? Great. All right, so then let's dive in. Thank you again for the chance to give this talk. It's really nice to see people here from a variety of institutions, and I will be transparent that this is surely the largest audience of people I've ever given a talk to that are not my own students or at a conference. So if I get a little bit nervous, please feel free to slow me down a bit with a well-timed question. I will say to Clint's point, if you're feeling confused and want to interrupt, it's almost certainly my fault, and I will take no offense whatsoever at any questions in the interim, but I'm also happy to just answer questions at the end. I'm calling this talk today Effects on What Differential Item Functioning in the Context of Randomized Controlled Trials. I'm going to start with just a really brief introduction, both to myself. So I do typically go by Sandy. So, no one has called me Sanford except my grandmother in a long time. And I'm happy to, absolutely be addressed by my first name. In fact, strongly prefer that. I'm coming from the University of Delaware, as Clint mentioned, and I won't recapitulate my research interests because his generous introduction covered them in more detail than I did. I do want to note that today's talk is based on a paper that was recently published in JEBS called Causal Parameter Moderation, Applying Moderated Nonlinear Factor Analysis to Causal Inference with Latent Outcomes. The framing of today's talk, I'm going to try to make a little bit maybe more general than the focus of that paper. Definitely will cover the same ground, but I'm going to sort of start from a maybe not from the assumption that everyone is necessarily familiar with what I'm going to be talking about, which I recognize is sort of somewhat niche within the broader world of quantitative methods. So we're going to start with the idea of experiments with latent outcomes. In a lot of fields, education, certainly psychology, political science, outcomes are often latent. And what I mean by this is just that we can observe them only indirectly through responses to items or other sorts of stimuli that we hypothesize are driven by some sort of underlying latent outcome. These can be things like reading fluency, depression, political attitudes, etc. Things where there's no ruler that we can hold up to someone's brain and measure how well they can read. What we can do is ask them to perform tasks under the assumption that the reason that different people perform better or worse on those tasks is because of the latent variable we're interested in. And the most common approach to estimating causal effects on latent outcomes in RCTs would use observed scores as the outcome. Now, it's been widely discussed, including by people on this call, that scores used as outcomes do have measurement error that biases effects towards zero. It attenuates the relation between the observed scores and status in treatment or control. And researchers have a variety of methods available for correcting this. Some of those methods might include things like errors in variables regression or regression calibration, reliability corrections in a structural equation model, which are under the hood essentially the same thing as EIV regression, or what is sometimes called a full latent variable model, which also allows for more flexible relations between the individual items and the score or the underlying latent variable than the use of sum scores, which are taken from the observed item responses. And another important piece of background that kind of sets up the aim of this work is that there's increasing interest in heterogeneous treatment effects in the context of experiments. So this is about heterogeneity with respect to the person side of the model. You can think of this as moderators of a main treatment effect of interest. Things like, is an educational intervention more effective for students who scored higher or lower on a pretest, or is a depression intervention more effective for younger or older individuals? These sorts of questions. It's taking that treatment effect and conditioning it on some sort of relevant background variable and seeing if the answer to how well the intervention seems to work changes with something that we can observe. Now, this is a visual depiction of models that we might use in kind of that full latent variable sense to capture these types of research questions. So on the left, we have a model that's being used to estimate the effect of a treatment on an outcome that has observed indicators in the form of item responses. So here, our outcome sitting in the middle is in a circle. That means that it's latent. Our treatment in a square or a rectangle means that it's observed. And so what this tells us is the treatment is treated as a cause of the latent outcome, which in turn is treated as a cause of the observed item responses. So these arrows are drawn in sort of the SEM sense of a cause in the context of the model. That does not necessarily imply that there's a causal warrant. Although in this case, because the treatment is randomized, we can make that claim. And then on the right-hand side here, we would use this type of model to investigate heterogeneity with respect to some particular covariate. And so we have augmented this model with a variable for the covariate and a variable for its interaction with the treatment. And you might see this name, it is named a bunch of different things, depending on sort of which corner of the literature you find yourself in. This could certainly be described as a structural equation model, could be described as a latent regression model, an IRT latent regression model, or a path model with latent variables. These are all just sort of different terms that you might see used for this general modeling endeavor. And what this lets us model is simultaneously relations capturing causal effects, which are sort of the top half of these diagrams, the relation between the covariates and the treatment and the outcome itself, as well as the relations from the latent variable to the items. And so in principle, what this is letting us do is correct for measurement error and for potentially unrealistic assumptions of classical test theory if the alternative is to use a sum score. This is letting us model some more flexible relations between that premise, the outcome that's sort of the premise of our latent variable model, and then the observed items that we can actually, code and see in our data. But we don't get there for nothing, right? There is a cost associated with using this kind of variable, which is that it implies numerous testable assumptions about the interplay between the effect of the treatment, which is the structural portion of the model, and the way the items reflect the construct of interest, which is the measurement part of the model. And the main assumption here, which I've phrased in a few different ways, is that the items are interchangeable indicators of the latent variable. This can also be phrased as the idea that the latent variable fully mediates the relation between the treatment and the items. You can think of it as a set of exclusion restrictions that prohibit direct paths from the predictors to the items. You can think of this as the items being invariant to treatment and any predictors of heterogeneous treatment effects, or you can think of it as at every cross section of the predictors in the model, the items measure the outcome the same way. And so just to illustrate what one version of this phrasing looks like, here we're going to run with the idea that the model is assuming the effect of the treatment on the items is fully mediated by the latent variable. And this has been discussed in a number of recent papers. And this is one way of depicting what violations of this might look like. So the most widely previously discussed violation that you might see is the idea that the treatment directly affects some of the items, which can be described as treatment-based uniform differential item functioning. That's one of, again, several ways you can describe what's going on here. And that's shown in, can you see my cursor? Cool. So that's shown by these red paths here. These are potential threats to the idea of full mediation. So on the left-hand side here, we'd see the only path from treatment to the items goes through the outcomes. When we introduce these red paths, the relation captured by this arrow here no longer fully describes the relation between the treatment and the items themselves. And so what this leads to is essentially a threat to the interpretation of this intended model. But this is not the only threat. So additional exclusion restrictions are that the treatment doesn't moderate the relation from the latent outcome to the items. So this could also be phrased as the idea of no non-uniform differential item functioning. And there is also generally an expectation that the latent outcome has a homoscedastic residual. This is just saying that the residual variance of that latent variable is the same across levels of the predictors. And violations of these restrictions in a strict sense make the model misspecified. Now, the kind of the diff that I'm describing, it may or may not be construct relevant. I'm not saying that this is automatically what I would call bias, but it's certainly a sense in which the model is not capturing some aspects of the data that under certain circumstances can lead to interesting findings. And that's what I'm going to be talking about. So at a high level, what makes up a measurement model in this context? Measurement models are generally made up of a distribution for the latent variable and then parameters that relate the latent variable to its indicators, which are the items. And treatments can affect any of these parameters, is the premise of this work. If the treatment affects the mean of the latent variable, that's what we would call mean impact in like a diff. In the diff world, that would be mean impact. And this is what we usually care about and what we estimate in that latent regression model where all of the exclusion restrictions are assumed. But you can also have a situation where the treatment affects the variance, which we would describe as variance impact or heteroscedasticity. This is not as commonly modeled, but it's still a type of impact on the latent variable as a whole. But then you can also get into a situation where the treatment affects the individual item parameters. And this would be described as differential item functioning with respect to the treatment. And these are all examples of what I would call parameter moderation. I certainly didn't invent this term, but I think it's a nice general term for what's going on here, which is the measurement model has a set of parameters consisting of a distribution and item response functions, and those change depending on the levels of the predictors. So one way that this can look is, let's assume that the item responses are categorical, and further, let's assume that they're binary. They take values 0 and 1. The item parameters generally express relations on the log odds or logit scale. So a prototypical two-parameter measurement model might look something like this. We have two equations here. The top one is saying that the log odds of a correct item response is a function of the latent variable eta, where I indexes people, a slope on that latent variable, lambda, and then an intercept for the item on the log odds scale. And then on the bottom, we have a distribution for our latent variable, which we're just assuming is normally distributed with a particular mean and variance. Now, what parameter moderation in this context looks like is this. So this is a path diagram that's illustrating all of the different potential moderation that could be happening in this latent regression model. Now, this model is not identified. I'm not saying this is what we're actually going to estimate, but what this is pointing out is that with the treatment as our sole predictor, we can have the treatment driving effects on the mean of the outcome, which is this black arrow, and that's typically what we're sort of hoping to interpret. And then we also have this yellow arrow showing that the treatment can also affect the variance of that residual. The green arrows tell us that the treatment can affect the slope of the item on the latent variable, also thought of as item discrimination. And then there are direct paths from the treatment to the items, which are that uniform diff or sort of item-specific effects above and beyond the latent variable. There's been a nice amount of recent work related to these assumptions, including by a good amount of it done by Josh, who is on the call and whose presence I appreciate. And the framework through which Josh approaches this is called item-level heterogeneous treatment effects. And so the premise of ILHTE models is that treatment-based diff can be thought of as a pervasive and randomly distributed phenomenon. Essentially, items vary randomly in their sensitivity to a treatment. And what this is essentially an additional source of uncertainty in the spirit of generalizability theory. This is estimated via an explanatory item response model. And most of the sort of most visible work in this area so far has focused on difficulty or intercept diff in a random items Roche model, but it absolutely can be generalized to include a slope and or a discrimination, as well as heteroscedasticity of the residual. So the real thing that's going to differentiate what I'm going to talk about is the premise that sometimes those item-specific effects might be sparse. That is, they might only apply to a few items and for reasons that I think are potentially fairly widespread in education. So when would diff in an RCT context be sparse or thought of maybe as a fixed effect or only applicable to some items? Here are some potential explanations for when that might happen. Scenario one, you have a very targeted intervention, but a very general outcome. And one example of that might be a math intervention focused on higher order thinking, as measured by a year-end state math test with many low depth of knowledge multiple choice questions, and if there's a typo, I should say, and a subset of higher depth of knowledge extended problems, which is a fairly common design for this type of outcome measure. Another possibility is a targeted intervention with a researcher-developed outcome. There's been a fair amount of research on this in the past couple of years, the differences in effect sizes we see between standardized and researcher-developed outcomes. An example of this here might be you have a reading intervention that uses a passage focused on dinosaurs and an outcome measure made up of some items on this topic and some on science more broadly. And that this previews the focal analysis that I'll present at the end of this talk. And in general, the subsets of items, in this case, might be thought of as sort of over-aligned to the intervention. And I use this term really in as non-judgmental a way as possible. It's just that there's a difference in how closely aligned some of the items are to an intervention than others. And then another possibility is that you have the interaction of the treatment with a background variable. And here it's essentially just layering on the possibility that some of the items might show larger effects for example, respondents with lower pretest scores. Like items may vary non-randomly in the extent to which the gains are sort of might be larger for students who started from a lower point on the scale, something along those lines. So when does this matter? On my view, it matters most, it will be most consequential when the diff is mostly or entirely in the same direction, or what is often called asymmetric diff. This is the idea that those item-specific effects above and beyond the effect on the latent variable as a whole are all moving in the same direction. Like there's a subset of items that are all extra sensitive. If it's a mix of items that are more sensitive and less sensitive, it really doesn't make that much of a difference to the end result. And I'll briefly mention a simulation that speaks to this. But if things all move in the same direction, and it's not modeled, what it will do is it will pull the estimate of mean impact in the direction of the diff. And there are some cases in which this can be considered bias. It certainly, in my view, is at least sacrificing interesting information to not investigate this and to move straight to a model that assumes invariance across treatment conditions. And this is really closely related to how researchers describe what it is that they're estimating an effect on. So if a fractions intervention were to lead to large gains on fractions items on, say, a state test that are not modeled and are instead absorbed into an estimate of the overall effect on math ability, you'll end up with what could be arguably be described as an overestimate of the effect of an intervention on math as a whole. Not because that effect isn't there, but because it applies to a subset of the items and it's harder to generalize that effect. So, if you model just mean impact, that implies that the effect is generalizable to whatever the full set of items measures. And in this case, that's not what's happening. It doesn't mean that the effect doesn't exist or that things are illusory, right? Like there are still effects. It's just that in this case, they're really just different things, and we can estimate them jointly within the same model. So to tie this now back to the specification of a model, in my view, one way that this can be thought of is as random versus fixed effects. So the work that Josh has done that I think has really moved our field forward in a meaningful way has been mostly based on applying a random effect for treatment-based diff that produces an average treatment effect that does marginalize over the individual item effects. Now, one thing that Josh has introduced that I think is very important is the role of item covariates. Here we're talking about a scenario where we don't have item covariates, or maybe we're not sure what characteristics of the items would be driving the phenomena that we're investigating. And in the case of asymmetric sparse diff, this type of model doesn't produce what you would really think of as a correction for bias. It might achieve some degree of correction via shrinkage, but it's really just not built for this purpose. And so the aim of this work is to expand the researcher's toolkit by bringing a fixed item perspective on the same general phenomenon. And what this can do is separate out items that are extra sensitive to the treatment from those that are not, at the expense of needing to estimate potentially many more parameters. And the framework we're going to bring to bear on this problem is called moderated nonlinear factor analysis. So what MNLFA does is it generalizes factor analysis models to write all of the parameters of the measurement model, both the item parameters and the distribution of the latent variable, as functions of an arbitrary number of observed covariates, treatment being one possible example. So essentially, you can think of the parameters themselves as being part of regressions on observed covariates. This was originally used in integrative data analysis, which is the field of taking sort of similar but sometimes non-identical outcome measures from different studies and figuring out which ones can be treated as interchangeable or not. And then it was reintroduced in the context of diff and measurement invariance a little bit more recently. And here are kind of the basic model equations that make up an MNLFA in the context of that two-parameter logistic measurement model. So here, the measurement model itself has been expanded to add a subscript I for person to essentially every term in the model. So now slopes become person-specific, item intercepts become person-specific, and the distribution of the latent variable becomes person-specific as well. And the way this is achieved is through these expressions here, where I've tried to color code to show you which one is associated, like which part of this diagram is associated with each equation. But the idea is that this is just saying the intercept for a given item is a function of a baseline value and an extent to which each covariate in the model is associated with a change in that intercept. And then the same goes for the slope, the mean, and the variance. And so what this does in the context of an RCT is it lets us generalize the factor analysis model that we're using for measurement to account for all of the exclusion restrictions that I previously mentioned. And so in the case that diff might be sparse rather than pervasive, this does align the model a little bit better with the hypothesized data generating mechanism than an ILHTE model. And as I'll get to, I really do see these models essentially built for different things and as complementary rather than like in competition with one another. So here the items are going to be fixed, not as random, and then diff parameters are going to be estimated individually without assumptions around the distribution of those parameters. People in this model, I want to be clear, are still random residual of observed predictors. That is very common in the IRT literature. Most of the time, IRT models are estimated with random persons. Same goes for factor analysis. Here's just the expression of what this model looks like for binary items with one variable, just treatment. So here we have this extra term where the treatment is potentially moderating our item slope. It's also potentially moderating our item intercept. And then it's potentially also affecting our mean and variance of the latent variable distribution. Now, this model isn't identified if we try to estimate all of the potential moderation at once. And just from a conceptual standpoint, estimating all those moderating parameters at once kind of just throws away the idea of the latent variable entirely because everything about the model now becomes person dependent. What we're really looking for in this case is a subset of items that may be interesting, not effects on every single one. And so to achieve identification, we need to do a few things. Number one, as in any latent variable model, we need to set the scale for the latent variable. This is no different from any other factor analysis or IRT model. We need to either fix the baseline variance or one baseline item slope, and we need to fix the factor intercept or one item threshold. But what we also need to do, because we're in a diff context, is find at least one, and ideally more than one, anchor item to estimate the model. Because sparse diff would tell us that most of those diff parameters, this here and this here, a lot of those should be zero. That's kind of the premise of the model, is that most of these items are invariant to the treatment, and they are fully mediated by the latent variable. There's just a subset that might not be. And so then the question becomes, how do we choose? And the paper describes one potential way of doing this, called regularized moderated nonlinear factor analysis. This is a penalized maximum likelihood procedure. And what it effectively does is it drives a lot of those diff parameters to zero using what's called the lasso, the least absolute shrinkage and selection operator penalty, which penalizes the likelihood as a function of the deviations of the individual diff parameters from zero. So the general idea here is that only the diff parameters that really improve the likelihood are going to be retained, and the rest of them will be driven to zero as the model converges via this penalized ML procedure. And then the parameters that get driven to zero, that tells you which items can be treated as anchors. So this is used in the example in the paper for initial anchor identification, followed by estimation of a model with those anchor items using standard maximum likelihood. And then further inference from there is possible. It's a little bit unprincipled because it's a post-estimation inference procedure. And I do talk a little bit about potential future directions to kind of clean up this part of the procedure a bit. But based on simulation, it seems to work at least reasonably well despite issues of multiple inference across multiple models. The simulation studies that I conduct in this paper, I'm just going to really briefly describe. They're sort of a small and targeted set of simulations because previous work has investigated the performance of regularized MNLFA across a lot of different conditions. So what I simulate is a situation where we have sparse diff that's asymmetric. That is, the diff is all in the same direction. A situation where there's sparse diff, but it's symmetric. So in expectation, the diff has an average of zero. Symmetric pervasive diff, which is diff gets applied to every single item following a normal distribution. And then a second study where I introduce heterogeneity with respect to one continuous covariate. And in that first set of studies, I compare MNLFA with anchor item selection based on the lasso, the ILHTE model, and the latent regression model with invariance assumed. So this is the model that imposes all of the exclusion restrictions a priori. what we find is that when diff is asymmetric, the MNLFA approach yields lower bias on that mean impact estimate than the ILHTE or the latent regression model, and much improved coverage. So here we can see there are two versions of the MNLFA due to that trimming step that I very briefly mentioned, and I'm happy to talk more about if people are interested. And comparatively, the bias of these two models is several times larger. And similarly, the coverage here right, hovers around 0.95. Here it's down around 0.4. And this is expected because the data generating mechanism is really not the one that either of these other two models would be ideally used to handle. Sort of moving from condition 1 over to condition 3. In condition 2, this is where the diff is sparse and it's symmetric. And you can see here that the bias is relatively low for all of these models, and the coverage is more comparable. What this tells us is that it's really that asymmetry of the diff that leads to differentiation in the answers that these different models give you. And then when we move down to condition 3, we can see that the ILHTE model delivers on exactly the promise that it makes, which is that when diff is not sparse, when it's pervasive and normally distributed, this is the only model that achieves anything close to nominal coverage. The bias is not really an issue here because the diff is symmetric. That's bias in the aggregate though, right? That's bias across replications of the model. Any one model is unlikely to really cover the true value very well in the MNLFA framework, but the latent regression model does even worse. So what this tells us is, in general, both of these types of item level effects above and beyond the latent variable do warrant consideration, and the latent regression model is not really going to do a very good job of capturing the things we care about. That second study that introduces some heterogeneity with respect to a continuous covariate. Here what I'm doing is just comparing that regularized estimation procedure to that latent regression again, as well as the true data generating model. And this is because the true data generating model is unknowable in practice, right? Like we don't get access to the true model, and it really doesn't often make sense to even think of there being a sort of a true data generating model. There's a model that we use to simplify reality in a way that we hopefully, that we hope will help us understand it. And what this shows is that the estimated models based on procedures that are available to us in practice using regularization does get much closer to the correct model than the latent regression model. So here you can see, for example, the bias of mean impact with respect to the treatment is 15 times the size in the latent regression model as it is in the MNLFA models. The correct model, as we would hope, is completely unbiased. And this is similarly true, although to a smaller extent, for the parameter that represents mean impact with respect to heterogeneity with that pretest. So this is the parameter capturing how much the mean changes above and beyond the main effect of the treatment based on someone's pretest score. And similarly, there are issues of undercoverage and bias in that latent regression model highlighted here. Sorry, I've been using my cursor on the wrong screen. Hopefully this, I guess it hasn't been confusing enough for anyone to interrupt me, but you can always revisit these at the end if you'd like. Very briefly, I will note that diff recovery in the simulation studies is good. The regularized procedure exhibits really, really high sensitivity, specificity, positive predictive value, and negative predictive value for diff by treatment. And it doesn't mask that pervasive diff in that third simulation study when it's present. So it can sort of be thought of as a procedure that might flag the appropriateness of that ILHTE model instead of the MNLFA. There is somewhat lower sensitivity for diff by pretest, but of course, everything is a function of what we simulate, and those effects were simulated to be a little bit smaller. The main thing I do want to point out is that even just capturing some of the larger diff effects does appear to meaningfully improve the estimate of that mean impact parameter. So the next thing I want to present is an example of applying this to a real data set. So this is data from a randomized controlled trial of a reading intervention that I retrieved from the Item Response Warehouse, a large public repository of item response data under the name Gilbert Meta 12, because this is one of the data sets in a meta-analysis that Josh conducted. It consists of a little bit over 2,200 second graders' responses to 12 binary or dichotomously scored science vocabulary items. And the reading intervention was focused on the study of mass extinctions. The item format was circle two words that go with, and then what differentiates the items is the individual word used. And the words were carnivore, extinct, fossil, etc., theory, hunter, organism, words that relate to different extents to the reading intervention. And so I analyzed this data set for parameter moderation for diff with respect to treatment status, a centered and a standardized pretest variable, and their interaction. And what I found was evidence of 5 items that are invariant, 1 that was less sensitive, and 6 that are extra sensitive. And that's shown here in this plot. So on the left-hand side, we have the initial estimates, and then on the right-hand side, after trimming some of the items based on corrected p-values of the diff parameters, we can see that most of the effects here are with respect to treatment status. There are a couple that are with respect to baseline, but I'm going to focus on treatment status here. And these are items that we would say are sort of extra sensitive to the treatment compared to the items that make up that invariant baseline. So it's always in comparison to the invariant baseline. And so what items are these? These 2 up here that show the largest effects, those are carnivore and fossil. The next largest would be theory and paleontologist, and then after that we have organism and trait. On the other end of the spectrum, the item that was less sensitive to the treatment was evidence. These are all effects on the intercept of the item. So this tells us that essentially above and beyond treatment status and the effect of treatment on that main latent variable, there's an additional fixed change in the logit of a correct response, the log odds of a correct response in the treatment group for these items on their own. Now, we do also have a slope effect. These are generally going to have less of an influence on the mean impact. They will affect the variance impact. And what they tell us is that this one particular item, the item where the word is theory, has higher discrimination in the treatment group. So this means there's greater differentiation in the treatment group between high and low performers than there is in the control group. Now, what did this modeling exercise do for the main effect that we might otherwise have focused on, which is mean impact in a latent regression setting? It cut it in half. So here we have the 3 estimates of that, point estimates and their standard errors for the mean impact of treatment on outcome. If we ignore all of the diff that I was just talking about, this value is 1.3. If we try to account for the diff, the value is 0.74 or 0.69, depending on this trimming exercise. In terms of variance impact, these are all in log units, so the interpretation is a little bit weird, but what I want to just highlight is that there's some imprecise evidence of greater marginal variance of the latent variable in the treatment versus the control. So just saying that conditional on treatment effect, there's a little bit more variability in that underlying latent construct that we're interested in, and that there's lower marginal variance with higher pretest scores. So the impact of the treatment can be thought of as maybe more uniform across individuals at higher pretest scores. And so at a high level summary, what we might say is that this analysis suggested that only about half of the items on the outcome measure can be viewed as indicators of a coherent latent variable for science vocabulary across both treatment and control. Ignoring this would have led to a mean impact estimate that was about twice as large, and that there was also some limited evidence of heterogeneous treatment effects across the items, no HTE on the latent variable mean. So that's kind of like the full high level summary of what we found. And then what we found is that other half of the items vary substantially in sensitivity to the treatment. So receiving treatment increased the log odds of a correct response, for instance, to that carnivore question by 1.53 logits, above and beyond the mean impact, which also drives change in this item. In log odd terms, that's a really large non-generalizable effect on one particular item. And I do want to emphasize that in terms of the model specification, these non-invariant words do still reflect the latent variable in the model. They're still responsive to it. They just do so differently depending on the levels of the covariate, in this case, primarily treatment and control. And what I want to note is that this is not really in conflict with the original study. So the author's original findings also included a note that they found much larger effects on words closely related to the intervention versus not. This is not meant to be like a reanalysis that's like a gotcha. Hey, this was wrong, this is right. It's more illustrating a way that we can kind of bring this observation into the latent variable framework. So the mean impact estimate in this model represents effects on the items that are less aligned to the intervention. I want to be clear, we do still see a significant and fairly large effect on the mean of the latent variable. So this tells us that there were gains on the less sensitive items as well. But then the original study found no evidence of effects on broader reading assessments. So the information we got out of this analysis might help us make sense of this, which is that there's sort of a gradient of sensitivity to the treatment. And some of these items exist sort of at that intermediary between super, super sensitive because they're very highly aligned, and really not sensitive at all because the broader outcome measures are very, very broad, and that there's a set of items sort of at the intermediary of those two places. And then the other thing that I'll note is just that the original study, their finding was based on an a priori separating of the items, and the regularized procedure that I used did not require that a priori separation. And in some real data settings, my suspicion is that there won't be such a clear explanation for why the items might differ a priori. Things like researchers who maybe create outcome measures and don't recognize the alignment that they're creating to the treatment, and that the procedure I've outlined could be useful for kind of a sensitivity analysis in that setting. And the last thing I want to just mention is that I do see this more as a general workflow than like a set of specific steps that everybody needs to follow the same way, and that it really starts with thinking hard about the outcome measure. So what the parameter moderation that this framework can capture means and how it affects generalizability is a function of the composition of the outcome measure. So if the aim is to analyze effects on the latent outcome, we generally wouldn't want to find any item-specific effects above and beyond impact on the latent variable, on the mean of the latent variable. That would sort of be the target of inference. But let's say that we have two sets of items, some general items and some highly aligned items. Whether this was on purpose or not, the procedure I've described will be sensitive to them. What I want to highlight is that if the measure is made up of more than half highly aligned items, then the main effect on the latent variable captures the less generalizable outcome. And so what this leads to is the idea that the analysis is not ever going to be fully informative without considering which items form that baseline invariant fully mediated subset. There's sort of no way around a deep understanding of the outcome measure. From there, that's when you can sort of get into the quantitative part of the study. And I do think it is worth considering potential covariates for heterogeneous treatment effects, but there's also a nice piece by Paul Van Hippel and Brendan Schutz talks about not overdoing it, not looking for heterogeneity if we don't have a good reason to. And power is always going to be an issue. I think some people get maybe mad at this for good reason, but I think one of the things I've encountered in working with real data is that sometimes if covariates are plausibly uncorrelated, it can be better to analyze them in separate models than together, even though ideally what we would do is include all of our potential predictors together. Just pragmatically speaking, this might be a necessary place to just sort of, bite our tongue and have to move forward. Then from here, once the data are collected and any relevant predictors are observed, that's when we can evaluate the data for anchor items. And what I want to highlight here is just the regularized procedure that I used is one way to do this, but it is not inherent to the framework. The paper discusses some other options, one of which is to choose a subset of items a priori, and having a strong understanding of that theory behind the outcome measure can be a good way to inform that a priori selection. And then from there, that's when we specify the model and interpret it. So the model specification and interpretation really comes after what I hope will be a lot of deep thinking about the outcome measure being used and how it might relate to the intervention. As far as future directions go, I mean, I think there are potentially a lot of different ways to think about extending this work. One of them is to constrain diff parameters to understand if the treatment-based diff that we find or demographic-based diff in a more traditional test fairness context can be thought of as systematic across items based on their content or truly item-specific and fully non-generalizable. There's also been some nice work on Bayesian approaches that account for uncertainty in the selection of the anchor items themselves. This sort of reduces the issues of post-estimation inference that you get from the procedure that I used. And I'm definitely interested in pursuing that. And I will say Clint and I have been collaborating on some work that sort of covers both of these bullet points. I'm also very interested in nonlinear modeling of the effects of those continuous covariates. So everything in this paper is linear. That's often an assumption that can be challenged, sometimes with important consequences, sometimes not. But I am working with a colleague on spline-based approaches to modeling nonlinearity of the covariate effects. I'm also really interested in just how the variables are coded and what this does for interpretation, in particular, potentially considering effect coding and the way that changes the interpretation of mean impact, because it then treats diff as an offset from the average rather than as something that's attributable to just the difference between treatment and control. Obviously, it doesn't affect model fit. It leads to all of the same implied probabilities, but the interpretation of that mean impact might change. So I'm interested in considering that. Thinking about maybe extension to some quasi-experimental designs like instrumental variables and better handling of clustering. So that regularization procedure I described, as currently developed, can't handle clustered data, and that is almost inevitably an issue in educational settings. So I'm interested in figuring some stuff out on that front as well. And that's all I've got. So here I have a QR code for the paper. It is also available as a preprint, and I'm more than happy to hear from anyone who's potentially interested in talking about this. And thank you again for the chance to discuss this work. I've really enjoyed it, and I'm happy to chat now. Thanks again.
So, thank you so much, Sandy. If anyone has questions, feel free to unmute or put them in the chat and I can read them out loud. We have one from Josh.
Hey, Sandy. Great stuff. We've talked about this work before, obviously, but great to hear you talk it through. I did want to ask about one thing that you mentioned towards the end when you have sort of like more than half of the items exhibiting this. Like, I'm imagining a case, let's say you have 20 items and like 15 are like over-aligned with the intervention. Like, what is to stop your model from attributing the diff to like just the less prevalent item set? Like, won't it just always attribute the latent variable to be like whatever most of the items are showing, whether or not that actually reflects the latent variable, or just a lot of items are showing diff in the same direction?
Yeah, no, that's exactly right. And so that was sort of the what I was trying to get at by talking about the importance of understanding the makeup of the outcome measure. This is a relatively exploratory technique, but I don't think we ever truly explore with absolutely no information about the data we're analyzing, or at least I would hope that's not something people are doing much of. And you're absolutely right. Like if the outcome measure is mostly super aligned to the treatment, then that's the latent variable that will be captured. And then the deviations that you'll see with respect to treatment, what you would expect to find is negative effects on a subset of items that are less aligned. And so that's why I was saying that you really can't get out of interpreting things relative to the content of the items themselves. And I would still think that would be informative, right? Like I would still find that to be something valuable. It's just that in that case, maybe the thing that we would hope to generalize to is really not well represented by a given instrument.
Yeah, thank you. That was sort of what I had intuited, but I that makes a lot of sense. Thank you for the clarification.
Oop, anyone else have a question for Sandy? We do have one in the chat from Michael. So Michael says, two questions, how to type. Sorry, it's a lot. What implications does this have for item analysis and standardized test settings? Not RCTs, obviously, but still a place where items may have to be deeply vetted. For example, are there any implications this has potentially for examining things like classroom coverage, what standards teachers actually taught on standardized tests? And then the follow-up is to that math test example. A lot of the time when researchers are using test scores, we don't have the items. So for example, using like the CETA data set from Sean Reardon and his group. Is there anything done to examine potential impacts of these things without the items?
Yeah, thanks, Michael. Those are really both meaty questions and things I am glad to hear people thinking of in response to this work. So the first one, I'm also really interested in knowing exactly what you describe. So something that you could absolutely think about doing is trying to collect data on student opportunity to learn particular content in terms of kind of the alignment of items to particular standards, or maybe a level above the standard, things like classroom time spent on, say, numbers and operations versus geometry in elementary school math, and using that as a covariate by which you might expect to find item level heterogeneity. Absolutely, I think there's something to that, and these methods could for sure be applied to that exact question. Implications for the ultimate reporting of test scores, I think, are a little bit murky because, at least in my mind, the nature of reporting in standardized testing is really first and foremost driven by policy rather than by psychometrics. So there's often less room than people like me who get to sit on the sidelines want there to be to explore the best way to model psychometric data in standardized test settings because of the ultimate requirement for things like a total score that's represented on a common and reliable scale for all students. And so it might be more of something that would be of interest to researchers or a way to try to produce additional validity evidence for a score. But I'm not sure that it would ultimately affect how we score students. And then to the second question about using sort of course end or test level data, if all you have access to is an overall score, then other than maybe inspiration for thinking about threats to validity, I'm not really sure that these item level methods have much to offer. I will say that this is a factor analysis based method. And so if you have things like subscores, maybe on certain portions of the test, you could absolutely in principle apply these methods, the exact same workflow with a sort of a non-linear, like a standard linear factor analysis model for the subscores. Now, again, subscores kind of have a long history of being criticized as just less reliable versions of the main score. So depending on how unidimensional the test really is, there might not be as much there as one would hope. But at least analytically speaking, you could absolutely do this with subscores. I do see a question in the chat that this is based on MNLFA and not applicable for IRT. I do want to clarify MNLFA like, in the same sense that the categorical factor analysis model is isomorphic with the two-parameter item response theory model. Moderated nonlinear factor analysis subsumes monotone IRT models. So the example that I gave, you can think of that as being premised on the categorical factor analysis model or the 2PL IRT model. They really are the same thing under the hood. And in principle, you can use this with the 3PL and the 4PL, and those models can be estimated in some software. So I would not say that this is not applicable to IRT. It's not applicable to something like a diagnostic classification model, like a categorical IRT model. But I think really any monotone item response function would lend itself to this type of analysis.
A quick question too. You know, you talked a lot about power and how when you're estimating lots of parameters, you're losing, you do have sort of a higher burden for sample size. Do you have any general sort of guidance on how many respondents, how many items someone might need to do something like this?
Yeah, so the existing work on MNLFA has shown, as one might expect, that things like the discrimination of the items does dictate sample size requirements in terms of both the items and persons. My impression from those simulation studies is that if the interest is really in the item intercepts, which is what will drive the largest differences in mean impact estimates, those can be recovered with some degree of power at samples as low as 250. But obviously more is always better. And in particular, the regularization procedure I used has been shown to sort of suffer from power loss at low sample sizes more rapidly than some other approaches. The nice thing about regularization is that it's built from the MNLFA model, so it has all of the same flexibility, which in this case includes the ability to use multiple continuous or binary covariates. If you're looking across, say, just treatment and control, that opens up a whole world of additional ways of identifying anchor items that might be better performing at lower sample sizes. I would say in general, if you're not finding anything at a sample size that's around 1,000, then that suggests that probably anything that is there is not a big enough deal to really affect substantive conclusions very much. But that's very hand wavy because I don't have a broad body of my own evidence to point to.
Maybe another question then to follow up, sort of thinking about, sort of inspired by you saying, like, if you're not finding large effects, maybe they don't actually matter if you have larger sample sizes. How much do you think this sort of like heterogeneous differential item functioning matters, like in practice?
I'm going to do the thing that my students always hate and say it depends. But it really does. And unfortunately, what it depends on is what's actually going on under the hood. So if there's an RCT that uses like maybe a researcher developed outcome measure that
Mhm.
has a set of items that are very, very aligned to the intervention and some that are less aligned. Or alternatively, if
Mhm.
it's a standardized test and the intervention is pretty narrow, um, I do think there is a real danger in interpreting a narrow effect on a subset of items as an effect on a latent variable as the whole. And this is something that happens with, regression of some scores on treatment status, the same way that it does in a latent regression model. It's really not specific to that latent regression model. Um, and I mean, like there are a lot of effects in educational research that don't replicate, and at least as many in psychological research that don't replicate. And to some extent, our outcome measures are never as perfect as we want them to be, but I do think that maybe less attention is sometimes given than should be to just how imperfect they sometimes are.
Thank you. I think we have time for probably one more question.
I've got one if folks don't. I just didn't want to triple dip. Um, this is for your future direction one that you mentioned, Sandy. Just because I like randomly stumbled onto this a couple weeks ago, and next time I get to try and model something, I want to play with them. For the point you mentioned around trying some nonlinear modeling, I think you said you were looking at spline approaches. Have you played around with explainable boosting machines at all, in that effort?
That is a great question. No, I haven't at all. So we should talk more about what the affordances of that might be. Would you
Yeah,
mind
no, I
sharing a
think
little bit
that,
about
sorry,
how
go for it.
they might relate? Yeah.
Well, thank you all so much. I want to add that we have one more seminar scheduled for this semester that'll be taking place on April 29th. We'll have Hansel Lee coming from Stanford University. I dumped a link to our mailing list in the chat if you're not already on it. Please sign up. Super happy to have everyone here, and I want to thank everyone for coming out. So thank you so much, and thank you, Sandy.
Thanks everyone for coming. I really appreciate everyone being here. This is a lot of fun.